Hello, can you hear me? Okay. So thank you everyone for coming for this late afternoon talk. I'll be presenting a case study on using Spark Solr at scale, which is basically the Spark Solr library developed by LucidWorks, and how we built an architecture and framework around it to enhance search relevancy at Flipp. So let's get started. So a little bit about me. I work as a data engineer at Flipp Search team. My main responsibilities include building pipelines to support machine learning models, which mainly includes using Spark for machine learning at scale and developing solutions for data warehousing for large-scale analytics. We're based in Toronto, from where me and my team have flown in here today. So let me just quickly take you through the agenda. First of all, I'll tell you about Flipp and what we do. Secondly, the search experience within the Flipp app. Then we'll jump into the problem domain and how Spark Solr architecture helped us resolve those problems. And then we'll do a couple of deep dives. Then we'll jump into some improvements and key takeaways and lessons learned. So what is Flipp? Flipp is a retail technology platform that basically enables the brick and mortar retailers and shoppers, the household shopper, to connect and find great deals. On the consumer end, we enable our consumers to find great deals to save money on their weekly shopping. And on the retailers end, the retailers use our storefronts platform to do visual merchandising and give a compelling browse and search experience to our users. The Flipp app platform is used by over 90% of Tier 1 North American retailers. So the search platform at a glance. So we basically get on our back end about 2 million searches per day. We have about 30 million documents, which is our indexed or the content that we have in our database. And we're a team of 5 engineers who work on these technologies every day to make search great at Flipp. So let's jump into searchable entities. So within the Flipp app, you can search for 4 main entities. There's your merchant flyers, which is the flyers that is published by your weekly retailers that publish the deals that you want in your local area. You can search for flyer items, where you can, instead of searching for your retailer, you can search for, let's say, your favorite items, such as cheese or bacon or ketchup or any category that you're looking for. It can be electronics. We also support digital coupons, so you can search for coupons for your favorite brands or from your favorite retailers and get them redeemed at your retailers to save money. And we also offer online deal search, so for those retailers which offer this service for click and collect and home delivery. So let's jump into the problem domain. So before I deep dive into the problem domain, let me just take you quickly through some of the basics of how a search platform works or its evolution. So these are some basic stages that every search platform, such as Apache Solr, would go through. Stage 1 is like a basic keyword search, which is like your keyword search algorithm, such as TF-IDF, BM25. And then you have stage 2, which is like query taxonomy. So you can apply logic such as synonyms, spell correction, stemming, lemmatization to map partial matches to your queries to an entity within your search platform. Then you have query intent, where you basically supply signals to the search platform, so the search platform knows what you are actually looking for and filter out domain-specific entities or entities that it can recognize, which it is trained on. And finally, there's self-learning, where you use machine learning algorithms to train the parameters or fine-tune the parameters of your search application. Now, the first 2 stages are kind of like features which come baked in within the search platform. So it requires minimal effort by a developer to expose these technologies and use them to find relevant content. However, these 2 stages are not always enough. So we come to stage 3, which is query intent detection. And this query intent detection is basically the main stage where Spark Solr helped us conquer this arena and helped us leverage signals which are dependent on your domain to identify the query intent before you perform a basic search. So let's talk a little bit about more signals. So in the domain of search, signals can be divided into 2 different entities. You have your user signals, which are like interactions which the users have with your content. So it can be clicks, impressions, the search query that the user typed, It can also be the amount of time the user spends on a particular scroll position after searching for something and seeing content. And then there's content signals. This is the content metadata, which can be the name, price, description, the feature set of the particular item that's indexed within Solr. Another very important content signal that we're going to talk a lot about today is the product's category or the content categorization. But the main point that I want to make over here is that in order to make your search relevant, you need to combine these two signals at recall time. So you cannot do boosting on your user signals and content signals separately. It has to be done within the same layer to get the full advantage of relevant search. So let's look at some of the content signal challenges that we faced. So because we work with so many retailers across North America, one of the problems that we face is when we get their content, they do not have a uniform category structure. So let's say if we work with 1,000 retailers, we will have 1,000 different category hierarchies. Because of this, every item would have a merchant-specific category. And this makes it a very difficult problem to boost your content based on categorization. So let me show you an example. So let's say there's like Bose headphones on sale at your local retailer, and there's 2 retailers that are offering a deal on Bose headphones. Let's say retailer A is categorizing these headphones within its own product taxonomy. It's a 2-layer taxonomy. And retailer B is classifying it as audio and earbuds and headphones within its own taxonomy. Now, this might seem visually quite similar to the human eye, but when you want to boost content based on category, these 2 hierarchies are completely separate things, and we cannot utilize their product taxonomy to map to our category structure. So another challenge that we also face is we work with retailers that do not have a product taxonomy to begin with. So what do we do in that case? What happens is that, let's say there is a deal for kale that is available at a local retailer. Since this product is not tagged by the retailer, it's up to our operations team to tag this content under our taxonomy. So let's say our content team or operations team tags it as kale, which is correct. And then there's another deal for kale at another retailer, which is tagged as greens, which is 1 level above in our product taxonomy for kale. So this is the complete categorization hierarchy for kale. So as you can see, greens and kale, they end up in the very end. But even though they're the same product, they're categorized separately or in different layers. Now what ends up happening is that because they're the same item, but they have different categorization content signals, when you search for these items, they would not be side by side within the search results. So this has a negative effect on our search ranking. So let's look at some of the user signal challenges. We were not leveraging Solr's features to boost on a lot of popularity signals that we were getting from our clickstream. This was because we didn't have pipelines necessary to index our signals within Solr. Rather, we were doing our search ranking or content ranking into a separate predictions layer. As a result, we were not able to utilize a lot of syntactic sugar that Solr provides in order to boost our content based on, let's say, popularity. Furthermore, our query categorization algorithm, which basically was only able to categorize queries which it had seen before, and was not able to correctly categorize entities which had or partial or entities, let's say in this example, shredded cheese is a small variation of cheese, and it should have the same category as cheese has, but it was not able to do that. Secondly, the query categorization was also not deep enough. So let's say even if we did do query categorization correctly, the categorization was not deep enough for us to reap benefits from it. So let's look at an example for that. Let's say there's a deal for tomatoes on sale, which is, let's say, tagged completely to the end of the categorization. And then there's another kale salad with tomatoes that is also on sale. Now, when both these entities or these items enter into our index within Solr, and a query, let's say, comes for tomatoes, now that tomatoes would only be categorized to a certain level, let's say fruits and vegetables. Now, since both these items are also similarly tagged to the same level, there's no way to differentiate between these 2 things. So what will end up happening is if you search for tomatoes, you will have kale salad with tomatoes at the side of it, because tomatoes also occurs as in the name of kale salad. So what did we need to solve these problems? One thing that we needed was we needed to bring our machine learning, ETL, and analytics together. Analytics was for content analytics, which was used to answer a lot of complex questions about the type of deals that are available in an area. And because we were doing it in separate layers before, it was already quite a complicated structure, and it was not a simple task to do a proof of concept. Another thing that we needed to do was to combine signals now. Like in the start, I told you, user signals and content signals need to be mixed together at recall time in order to get boost on relevancy. We needed seamless Spark Solr integration. What this means is that I should be able to read my Solr collection within Spark as a data frame or a data set, and vice versa. If I have a data frame, I should be able to index that easily into Solr in a distributed manner. This is a very important point. We wanted to reduce our productionization time because before we had our recall layer, our predictions layer, and our analytics layer separately. So if you wanted to, let's say, prove something, do a proof of concept or try out a new search algorithm or do some cool NLP experiment, you would have to spend a lot of time to take it from prototype to production. This was because a lot of our systems were spread out and they were not so easy to organize, due to which it was also very hard to test systems together. And also, we needed it to be scalable and efficient. So if, let's say, our query load or our traffic increases by 10 times, the only thing I need to change is just adding more nodes instead of changing the algorithm. So it should be easily scalable. And of course, it has to be cost-friendly because that's something we strive for and makes the executive leadership very happy. So how do we go about in the Spark Solr journey? So we needed to make an action plan. The first thing was to get our content aligned with our existing category signals or the content signals. So utilize our existing content signals and bring all our content into our uniform category structure. And then persist that into Solr. And secondly, since our query categorization depends heavily on the correct categorization of our content, we needed our context or query categorizer to be also persisted within Solr. And finally, we needed both these entities, both the content signals and user signals, to be together within Solr. So when we perform a search, we can utilize both these signals at the same time. That will reduce latency. So let's go through the Spark Solr architecture. The first step that we do is when we get our content, we index the raw content within a Solr Cloud environment as a collection. Now what ends up happening is that this collection is then readable by the Spark Solr connector. And this content ends up in our Search ML and ETL platform, where we can do things like content categorization and aggregation, cleaning of data, cleansing, all those ETL tasks. Secondly, we have our user signals on an analytics layer, which we also can then read within the Search ML and ETL platform. These usage signals are stored separately and are sent by the app directly in order to track the usage of our app and how users are behaving. Finally, we were able to join, aggregate, apply, train our data with our popularity models and our content signals together, and then finally index that back into Solr, which is a surprisingly very fast process. And finally, once your model or your content is attached with the relevant signals it needs, it's ready to be searched, to be served with your backend. So user can just query Solr directly, and it doesn't have to go through a prediction layer. It just can predict, the predictions are already within Solr, and it can be served to the user to get enhanced search experience. And additionally, you can also write pre-processed data back to the analytics layer so that it can be further analyzed within Databricks or any other visualization platform to get better insights about user behavior. So let's do a deep dive into the content categorization. So this is what raw content in Solr looks like. So on the top over here, you see a Samsung TV, which is exactly the same Samsung TV, but from two different retailers. So if you can see, if it's big enough, the categories are different, like I told you in the start. And in the bottom, we have the two accessories or frames or stands that basically come with these TVs. So the problem here is that both these products are basically the same but different category structure, and there's noise that's attached with them. So when you would search for Samsung TV, you would see the TV with the frames. This is not what the user actually expects to see. So this is how our categorization algorithm actually works. So we would get the product metadata from, let's say, one retailer. And then that retailer would have a certain hierarchy. Now what we would do is we created a microservice to extract this category structure into category keys. And then we use that microservice to map, let's say, a category key to our product taxonomy. Now, obviously, we cannot do this for all the items, otherwise it would defeat the purpose of machine learning. So we would just create enough training data in order to sufficiently train our multi-layer perceptron network based on the feature of name of the product. So what we're basically doing is, let's say if there's 10 items under a certain category key, and I map it to our category taxonomy, then all those items under that taxonomy automatically get categorized to our product taxonomy. And now once I have this training data set, we're given, I give the feature the name of the item and given its product taxonomy under uniform structure, we can train it so that the multi-layer perceptron, when next time it sees a Sony TV, it can recognize that it's a TV and it should be categorized according to a certain hierarchy. Now, obviously, there are certain confidence levels that are attached with every level of the hierarchy. Therefore, we only pick up those predictions which we're actually confident about that were done correctly. So the workflow is something like this. So you index content into MySQL, and then you index the raw content within Solr. Then we use our microservice to get some data from the same MySQL database and input the training data within Solr in a separate collection. Now we read the raw data through the Spark Solr connector into Spark as a data frame, and we feed our training data to our classification model so that we can train it and then also get the categorization that is related to an item within data frame. And finally, we get our clickstream signals from our analytics layer and write the items categorized with popularity metrics back into Solr. And as a result, as you can see, the both same TVs are now categorized under the same category structure to a certain level, and with the item weight popularity signals attached to it. And the frames are categorized as furniture, so they can now easily be filtered based on the search result when someone is searching for TV. So let's look at understanding user intent. So before I tell you how we do it, I need to tell you why we should do it. So this is like a relatively old screenshot of someone searching for nuts on the Flipp app. As you can see, there's some guitars and car oil filters and some cereals that are coming up. And the only reason that they're coming up is their content signals or their keyword signals has the word nuts in it. Because you're not telling this platform what the user's intent is, you cannot actually take benefit from its correct categorization. As a result, you get bad results. So we use this concept of reinforced intelligence, where we use the user to tell us or label the data for us in order to categorize our queries. So the workflow is that, let's say the user queries something, and user sees a bunch of results. As a result, user will perform some actions. It can be a click, an impression, or a clipping. And based on that, we see the data or collect the data from the user to inform and train our query categorization algorithm. So let's see how the training works. So the basic question, what I want to ask is, what is the probability that a user will click on a particular category class given the query nuts? Now, this is a graph which shows on the x-axis the different categories that nuts can belong to for the search results that show up for nuts within our Solr index. Now, and on the y-axis are the number of clicks that users made for each category based on that search result. Now, the main point here is that one query can be associated with multiple classes, but due to our reinforced intelligence concept, we picked the category which has the highest clicks to be the category of that query. And what this basically means is the next time when I see or the app sees the query nuts, our query categorizer will categorize it as dried fruits because that's what the users thought is the most relevant category for that query. And then, how do we persist the query classifier? This is a model of how you can persist your classifier model within Solr. So you have your category hierarchy, and you have all the confidence levels attached to the query that tell you how confident we are in the prediction of a certain query's category. And as a result, you can see, now these are different variations of the word nuts. So you've got nut thins, you've got peanut butter. So it was able to correctly categorize nut thins as cereal and granola. And it was able to figure out that peanut is not actually a dried fruit, but it's nut butters. And over there on the rightmost side, we have the prediction confidence, which tells us how confident we were in these predictions. So the workflow would be, given a query, compute all possible category classes and persist those category classes as query domain-specific entities. Once you have the domain entity recognition model and the category classes, you have to persist them within Solr as a searchable field. Now, the advantage of this is that if you save or persist your queries within Solr as a searchable field, you can use Solr semantic features such as stemming or synonyms. So you can do, for example, matching on, let's say, someone types strawberries, but let's say you don't have strawberries indexed in your model. But if you use Solr stemmer, strawberries can be stemmed to strawberry. And the both query categorization can be achieved using strawberries and strawberry, which is basically the same thing. And finally, after attaching the signals, you query your model to get your query's category and boost your content ranking based on the query's category. And finally, we have collaboration. So you have your query intent signals ready, and you have your raw content ready within Spark. And once you have both these signals, you can index them into Solr. Now let's see how we measure improvements. So we use a measure in Flipp called normalized discounted cumulative gain in order to, and it is an offline metric which we use to measure our search improvements. This basically consists of three basic components. So cumulative gain is just that given a search result, how would you rate a result from very relevant to not relevant at all, from a scale of 0 to 2? And a cumulative gain of a search result is just the sum of those scores. Discounting is taking into account the positional bias, and which is basically saying a search result, if it's relevant, should be on the top rather than the bottom of the search ranking. Because if it's at the bottom, it's not very useful for the user. And normalization is just taking your ideal DCG or your highest DCG and dividing all the DCGs that you have for your search results by that. So let's take an example of how we saw cumulative gain improvement. So let's say there was a query for olive oil. Now previously, this was what the top 6 results for our olive oil query would look like. So you have some olive oils on the top, but then you have some olive oil in tuna, and then you have olive oil wax cloth, and some irrelevant items. So based on a reasoned assessment, this is what the cumulative gain score that I would give to the results of this. And this would be a total cumulative gain of 6. Now after the Spark Solr improvements, this is what our results look like. So you have all 6 olive oils. And as a result, you would give, based on cumulative gain, I think that they're very relevant. So I would give them a total score of 12, which is 100% improvement over the previous result. Now let's see some DCG improvement where we take the search ranking into play. Let's say there's a query for fish. So this is what the result would look like before. So you have, for by fish, we mean like we want to see raw fish that we want to buy. So you have some canned tuna on top, and the raw fish is more down in the search results. This is the DCG score that I would give based on the position and the cumulative gain. And let's say we have a cumulative DCG of 6.43. Now, after Spark Solr, you can see all the raw fish has now shifted to the top, and all the irrelevant items have been re-ranked to the bottom. So that means there was an increase in our precision. As a result, this is the scoring for DCG, and this is what the total for our DCG improvement would look like, which is very pleasing. So what are some of the lessons that we learned that while developing the Spark Solr architecture? So one thing that you need to keep in mind is that when Spark indexes Solr, it puts considerable strain on your Solr cloud nodes, so which can lead to a deteriorating effect on your P95 latency. So which means that maybe some of your users in the tail end might not get the results in time, or it might time out. So if you want to maintain the same level of latency that you had before with the Solr cloud, a good practice is to add some more compute power to your Solr cloud nodes. Another very good advantage that we get from Spark Solr is read parallelism. So Spark is very good at reading data from Solr. This is because if you match the number of shards in your Solr collection to the number of your Spark workers, you can basically, every shard will then serve a request from Solr for read. Now this increases the parallelism of reading as compared to a MySQL database, let's say, where if you don't do incremental reads, it can take a very long time. Secondly, you can use Solr predicates instead of SQL predicates to filter your data within Solr. So you can use the Solr params argument within Spark and specify the filters that you want in order to filter your data and get a smaller subset of the data that you want to, let's say, process or return. Finally, in our experience, if you're using multi-valued fields within Solr, it may require some extra processing because Spark does not index array fields correctly into Solr. So you might have to do some extra processing like exploding them or flattening them out. Another feature that Solr has is soft commit seconds, which basically means that as soon as I index Solr, my results should be searchable. Now, this is a very good setting for prototyping or if you're just using it in a staging environment. But in production, it can put considerable strain on Solr, so it's advised not to use that and use hard commit instead. And of course, if you have a large index size and your documents are very large, then Spark Solr has a setting of setting the batch size, so you should always prefer using a smaller batch size if you have a large index. So the key takeaways that I want to put here is that using Spark Solr, you can open your Solr collection and have it interfaced in Spark and then apply all kinds of machine learning activities or libraries that you want to do. Like let's say if you want to do NLP or deep learning. So it opens up Solr to be applied with all those great algorithms. It enables faster data analytics in Spark SQL than traditional SQL frameworks. So it's better if you index your data within Solr and read it rather than reading it directly from the database. And finally, storing text classification models, especially in Solr, gives you huge semantic benefits rather than storing them in, like let's say Redis or another cache layer. And that's it. Thank you very much for listening. I'm happy to take questions. Oh.
If you'd like to ask a question, please come to the mics in the middle of the aisle.
I have a question.
Yep.
Maybe it's a stupid question, but
Okay.
why don't you use Elasticsearch? Why do you use Apache Solr? Is there any design concerning or design trade-offs?
So over the years, you're right, Elasticsearch is also a very good option, but over the years, the Solr community has really grown. And it has been doing some great work within the NLP libraries. So it has been you can do a lot of better feature engineering using Spark Solr than Elasticsearch. Even though I haven't really dug deep into what Elasticsearch can also do that or not. But for feature engineering, Spark Solr provides you with its tokenizer factories and analyzers that really make it easy for you to choose the right features to train your search models.
Did you do partial updates or did you do atomic commits on Solr for?
Yeah, good question. So we basically use Airflow to run our DAGs for indexing Solr. So we only do delta updates because doing a full update would basically make the indexing process very strong. So since you have your Solr collection within Spark, you can find out which records were updated or which records are out of date that need to be updated within Solr. So you can do 24-hour delta indexing. You don't need to do a full index.
What kind of classification algorithm did you use for the category classification?
So we used a multi-layer perceptron network.
Okay.
So we can talk offline if you want and
Sure.
give you details about it.
I also saw LTR, learning to rank, over there. Did you use?
So we prototyped it. Our data scientists prototyped learning to rank. But in order for that to be effective, we need a very large feature set. It's something that we want to do in the future, but it's not in production right now.
Okay, thank you.
All right, let's give our speaker a big hand.